3.2.3 Common and Natural Logarithmic Functions. So we learned about these last year. So this is kind of an overview of things that we learned last year. But recall that the two most important types of logarithms are those of base 10 and those of base e. So we're going to talk about the graphs real quick. So the inverse function of the inverse function of the exponential function we know is a logarithm we learned last year. So we read this as log base 10 of y equals x, and it's called the common logarithmic function. And recall, when you don't have that base written, it's always assumed it's base 10. So let's go ahead and look at this side over here. We know that this is our exponential function. And the reason we know this is exponential is because it has a variable as an exponent. So this is base 10. And for this, we know that our reference points that we use are -1. So if I plug -1 in for x and I leave it as a fraction, I get 1/10. Because remember, when you have a negative exponent, that goes in the denominator. If I plug in 0 for x, I would get 10 to the 0 power, so anything to 0 power is 1. And if I plug 1 in for x, 10 to the first power is just 10. So I'm going to use these reference points because they help me actually graph my inverse. So recall that the inverse, you switch your x and your y values. So for my inverse function, I know that my x and my y values get switched. So this would be 1/10. So the log base 10 of 1/10 is actually equal to -1. The log base 10 of 1 is equal to 0. And the log base 10 of 10 is equal to 1. And again, we did talk about this last year, so it's kind of just an overview. So because they're inverses, we know that we are reflecting them across a line y equals x. And again, recall to actually find the inverse, you switch your x and your y values and you solve for y. So to find the inverse of this function, so we right now have y equals 10 to the power of x, so the inverse is x is equal to 10 to the power of y. And recall, this is what we learned last year. The only way you can solve for the exponent is to use a logarithm. So this becomes the log base 10 of x is equal to now that exponent y, because the answer to a log is always an exponent. And so over here we can do the same thing. So if we were to solve by switching our x and our y values, so in this case we get x is equal to log base 10 of y. The only way to get that y out of the log is to use exponential form. So the base always stays the base. So this is 10 to the power of x is equal to y. And so that would be the inverse. And as you can see, that's why these are reflected across the line y equals x. Some other things we need to talk about. So we just did, if you look down here at our table, let's go ahead and look at the domain. So if you look at our exponential function, we can see that our domain is going to be all real numbers because we can plug anything in for x. We don't have any variables in a denominator. We don't have any variables underneath an even root. So I know my domain for this is going to be, again, all real numbers. So -infinity to infinity. The range, however, you'll notice that if we plug in values for x and they are negative, we don't get negative answers because remember that just makes it a fraction. So if I did 10 to the -2 power, that's actually 1 over 100. And so that means we're just getting closer and closer to 0, but we're never going to be able to reach 0. So we said that there is going to be an asymptote, which is in this case horizontal asymptote at y equals 0. So because of this, that tells me my range is from 0 to infinity. And so if we look at our other graph, which is our logarithmic graph, for this one, we can see that the domain, notice that we do have a restriction because we can't take the log of negative values or 0. And of course, because we switch our x and y values, if this is a horizontal asymptote for the inverse, it becomes a vertical asymptote. So we actually have a vertical asymptote at x equals 0 for a logarithmic function. That means my domain is 0 to infinity, which makes sense because again, you're switching your domain and range. So this became my domain and this is going to become my range. So now my range is all real numbers, negative infinity to infinity. And so the next thing we're going to look at, as we talked about before, is our end behavior. So if I look at my exponential function, as x approaches infinity, notice that your y values are going up to infinity. And as x approaches negative infinity, right here, you can see you're approaching your horizontal asymptote, so your y values approach 0. For our logarithmic graph, as x approaches 0, because we can't go to negative infinity again because we can't take the log of 0 or a negative number, so we would say as x approaches 0, which makes sense because you switch your x and y values, our f of x is approaching negative infinity. And as x approaches, and this should say positive infinity here, I forgot to fix that. So as x approaches positive infinity, our y values are going towards infinity. And so that would be for the end behavior for exponential and logarithmic. So we've already talked about these reference points, and again, because the log is the inverse, those are going to switch the x and y values. So that's a way that you can help graph your logarithmic functions. So just recall that if we want to convert from exponential to logarithmic form, etc., for this, if we have the base and some exponent equals some answer, the logarithmic form of that then would be the log, the base stays the base, of the answer equals the exponent. And again, we did talk about that last year, so hopefully this kind of brings back some memories. Let's go ahead and put some numbers in there though. So let's say we have 5 to the power of 3 is equal to, we know, 125. So if I wanted to rewrite that in logarithmic form, that would be the log, the base stays the base, so the base over here is 5, so this stays 5. So log base 5 of the answer, which is 125, equals 3. So this would be the exponential form on the left, and the right side would be the logarithmic form, because remember again, the answer to a log is an exponent. And which is really cool because it allows us to solve for exponents. So we have our definition of our logarithmic function. So y equals log base a of x for all x values that have to be greater than 0. Also recall that our a values have to be greater than 0 and they can't be equal to 1 for a base for the log. And again, remember that y equals the log base a of x if and only if x equals a to the y power, because we have to be able to write it in exponential form. So if you want to just quickly test yourself, rewrite these in exponential form. If you want to pause it and then unpause it to check your work. So for this, if we rewrite this, we know the base is 25, so the base stays the base. So this would be 25 to the power of 1/2 is equal to 5. And for this one over here, the base is 7, so 7 squared is equal to 49. And both of those, of course, make sense, and you could always use your calculator to check if needed. We also have properties of logarithms that we learned last year. So if we have the log base a of 1, it's equal to 0. Why is that? Use your exponential form to help you. If I rewrite this in exponential form, this is a to the power of 1, and we know anything to the first power, a to the 0 power is equal to 1. So anything to the 0 power is what I meant to say is equal to 1. For this next one, we have a to the power of 1 is equal to a. So that's why the log base a of a equals 1. For this next one, our base is a, so a, and this is our answer, so a to the power of x is equal to a to the x, which is why log base a of a to the x is just equal to x. For this one here, this is just a statement. So log base a of x is equal to log base a of y if x is equal to y, so if and only if. And this is another property. So if I have a to the power of log of a to the m, it's equal to m for every m greater than 0. And if 0 a has to be bigger than 0, but it cannot be equal to 1. So just to look at this last power real quickly, if I were to rewrite this in logarithmic form, you'd see why this is true right here. So this is, of course, our base. So log of the base of the answer equals the exponent. So the log of base a of the answer, which is m, is equal to the exponent, which in this case is this whole thing, log base a of m. And that's why this property right here is true, because again, if you were to put this back into exponential form, you would get this. So you could always check your work putting it into one of the other forms. So it says we want to, without a calculator, find each of these values. So again, if it helps you to think about the exponential form, that is a good thing to do. So we're saying 6 to what power, because this is equal to something. So 6 to what power is equal to 6? Well, we know that by that property we just talked about, 6 to the power of 1 would be equal to 6. So this is equal to 1. Here, if the base is not written, remember that's base 10, so we're saying 10 to what power is equal to 1? Well, that means that 10 to the 0 power is equal to 1, so log base 10 of 1 equals 0, which again is a property. For this one here, so again, the base isn't written, so it's base 10, so we're saying 10 to what power equals the cube root of 10. And so remember, we can rewrite a cube root as an exponent. So this is really 10 to what power equals 10 to the 1/3 power. So that means that if these are the same base, we know therefore the exponents have to be equal. So that means the log base 10 of the cube root of 10 is actually equal to 1/3. For this next one, we're saying the base is 125 to what power gives you 5. So recall, in order to solve something that's exponential, if you can make the bases the same, it makes it a lot easier to solve. So 125 we know is 5 to the power of 3. So we're saying 5 to the power of 3 times what would give me 5. So really, remember this is 5 to the power of 1, so we know that if you have the same base, therefore the exponents have to be equal, so we can actually just solve this. So 3 times something is equal to 1, so divide by 3, so that something is equal to 1/3. So that means if we were to do 125 and to the 1/3 power, which means the cube root of 125, it's actually equal to 5, and you can of course use your calculator to check that. Over here, again, there's no base written, so we're saying 10 to what power equals -7. However, remember that we can never get a negative answer whenever we're working with exponentials, so this is not true, and even if you put it in your calculator, you're going to get an error, so there are no solutions for this one. All right, for the next one that we are solving, it says solve by using an equivalent statement. So for this one, we are trying to solve for the logarithm. So when you're trying to solve for logarithms, it's helpful to use, again, exponential form. So the base is 10 if it's not written. So we're saying this is 10. The exponent would become 5 is equal to x. And so you can just plug that in your calculator if you don't know. So this is x is equal to 100,000, because that's 10 to the 5th power. Over here, if this is in exponential form, the easiest way to solve for the exponent would be to use logarithms. So we're saying the log base 10 of 52 is equal to x. And for this, because it's base 10, we can go ahead and use our calculator. So on our calculator, remember the logarithmic button is right here next to the 7. So that gives us base 10. So we have the log of base 10 of 52, and all we have to do is hit enter, which gives us, and we're going to round using 4 decimal places, so 1.7160. So x is equal to 1.7160. So something else we talked about last year is natural logarithms. So natural logarithms are used quite often because we see this number e a lot in mathematics. So again, we did talk about that last year. So we know that base e, if I were to look at my reference points, just like we did for 10 to the power of x, so e to the -1 would be, of course, 1 over e. e to the 0 power, anything to 0 power is always 1, and e to the first power is equal to e. And of course, remember we learned last year that e is about 2.71, and of course there is that button on your calculator. So if we look here, we can see that e, you can use the division symbol to get e, or right here if you hit second and ln, that also gives you your e to the power if you want to use that. So for this, your exponential function, again, you can see that it has a horizontal asymptote, which we talked about in that table earlier. So we know there's a horizontal asymptote at y equals 0. Over here for our inverse, we have the natural log of x. The natural log of x is just the same thing as the log base e of x. Those two things mean the same thing. It's just that we use log base e so often that a natural log is just kind of shorthand way of writing that. So of course for the inverse, since this is base e, the inverse of that is the natural log. All we have to do is switch our x and our y values to graph this. So the x would be 1 over e. So log base 1 over e is negative 1. Or we could say the natural log of 1 over e is negative 1. The natural log of 1 is then 0. And the natural log of e would be equal to 1. And for this one, we know it has a vertical asymptote, just like our common logarithm of base 10. So we have a vertical asymptote at x equals 0. And if going to find the inverse, you switch your x and your y's and you solve. So for our inverse here, we have x is equal to e to the power of y. So if we write this in logarithmic form, the base stays the base. So log base e of y, I'm sorry, of x is equal to y, which is our exponent, because a log gives us an answer of an exponent. But because we use log base e so often, we can also write this as the natural log of x is equal to y. So these two things mean the same thing. So over here, we can do the same thing. We have x is equal to the natural log of y, and then we would put this in exponential form. So for natural log, that's always a base of e. So this would be e to the power of x is equal to, y. If it helps you to write this using log base e, that's fine. So x is equal to log base e of y, and then put it into exponential form, that's fine. It's the same thing though. So we have our properties of natural logs, which are very similar to the properties of common logarithms, except for we're just using a base e. So natural log of 1 is equal to 0 because e to the 0 is 1. The natural log of e equals 1 because e to the first power is equal to e. The natural log of e to the x equals x because e to the x equals e to the x. The natural log of x equals the natural log of y if and only if x equals y. And e to the natural log of w is equal to w. And again, that's because you can write this in natural log form, I should say, because this would be if you wanted to write it using the log. So log base e of w equals the exponent, which in this case is the natural log of w. And remember, we can write the log base e as the natural log. So the natural log of w equals the natural log of w. So that's why we can do number 5 there. So for the next one, it says use a calculator to find the natural log of 1.3. So that's just getting used to where is that natural log. So the natural log is right here, kind of next to that 4. So on my calculator, if I do the natural log of 1.3, notice I get 0.2623. We could also do the log base e of 1.3, and we should get the same thing. So if you have a newer calculator, you can do this, but if you don't have a newer calculator, you won't be able to. So if I go to math and scroll all the way down, some new calculators have the log base right here button. So if I hit that, I can actually put in other bases rather than just using this log button, which is always base 10. So now if I do second and the division, I can get e. And so if I do 1.3, you'll notice it gives me the same answer. It's just a lot easier to write the natural log of 1.3. So that's the same answer that we have right here. So the next one says solve each equation by using an equivalent statement. So again, if we want to solve a natural log or we want to use exponential form to help, the base, if it's not written for a natural log, is always base e. So this means e to the second power would be equal to x. So then you would just get your calculator out and you would do second, and the division symbol is e to the power of 2. And so that gives us 7.3891 if we round. So x equals 7.3891. Looking at the next one, this is an exponential equation, so we want to solve using logarithms, or in this case, a natural log. So if it helps you to write, the log base e of 8 is equal to x, that's fine. This is the same thing as the natural log, so we're really saying the natural log of 8 is equal to x. So on my calculator, I would just type in the natural log of 8, and that's going to give me my solution, 2.0794. So x equals 2.0794. Okay, so again, just kind of a quick overview of things from last year. So something else we need to talk about from last year is graphing our logarithms of any base. So when you're graphing a logarithm of any base, it's helpful to note the reference points that we used before. So we've already talked about those reference points in that first table that we had. So if you look here, these were the reference points. So these are the reference points for natural log and also an exponential form for e to the power of x. So if I go back here, so we're looking at the log, oh, it keeps doing that. So log of any base, and we're trying to solve. So we're saying this is y equals log of any base b of some value x. So these are the reference points that we use. So b1, this point, that's just an arrow. So the point here, and of course there's going to be a point here. So for your table, we know that log base b, so the log base b of b is equal to 1. So the reference point we use is b comma 1, which is this point right here. And again, because b to the first power equals b. So the next one is the log base b of 1 is equal to 0 because any b to the 0 power is 1. So then our next reference point is going to be 1 and 0. And then the next one we have is log base b of 1 over b. So b to what power gives you 1 over b? B to the negative 1. So 1 over b is going to be negative 1. So the next reference point is 1, 0, which is right here, and 1 over b, negative 1. So these are the reference points that we use when we are graphing. It makes it helpful. So it's just the base comma 1, 1, 0, and 1 over the base and negative 1. So let's go ahead and use that in order to help us graph these next three. So for this one right here, we know that the base is 4. So my reference points that I'm going to use are going to be the base. So log base 4 of 4 we know is equal to 1. And again, that's because 4 to what power equals 4 to the first power. And so for the next one, we would have log, so it's always going to be 1, 0, I should say. And the next one would be 1 over b. So 1/4 is equal to negative 1 because 4 to what power gives you 1/4? 4 to the negative 1. So log base 4 of 1/4 equals negative 1. So when I graph this, I have the point 1, 0, 4, 1, and 1/4 negative 1, which is about somewhere there. So my graph will go like this. And of course, don't forget to also graph your asymptote, which is at x equals 0. So then for the next one, if I want to graph something that has a base that's a fraction, we can do the same thing, just have to be kind of careful about how you write it. So again, just looking at these reference points, b is 1, so in this case b is 1/3, so log base 1/3 of 1/3 is actually equal to 1. Log base 1/3 of 1 is always 0. And the next one, 1 over b. So 1 over your b, which is 1 over 1/3. Remember, when you're dividing by a fraction, you multiply by the reciprocal. So this is 1 times 3 over 1, which is just equal to 3. So 3, and then this would be -1. So now our points have changed slightly. So we have 1/3 in 1, 1, 0, and 3, -1. So now our graph just is going this way, which makes sense because if you put this in exponential form, this is saying 4 to what power, and this one over here is saying 1/3 to what power. So remember, this would be exponential growth, so this goes this way, and this would give you exponential decay, so that's why this is moving the other way. But we still have that vertical asymptote at x equals 0. So for the last one, if you wanted to graph this real quickly, it would be, again, the same thing. So we have the base, which is 6 and 1. So log base 6 is 1. Then we have the log base 6 of 1 is 0. And 1 over the base, which is 1 over 6, gives you -1. So then you just plot these. So we have 1, 0. So 1, 2, 3, 4, 5, 6, 1, and 1, 6, -1. So my graph would just go like this. So it's kind of nice to use those reference points to kind of help you. And again, I'm just using these right here each time I do that. All right, so let's go ahead to the next part, which is looking at the transformations. So we've talked about our transformations before, so remember that these are the horizontal transformations. Horizontal transformations change your x values. A and K are your vertical transformations, which change your y values. And so these are the rules that we've learned. So let's go ahead and take a look at some equations. So it says describe the transformations from the log of x to 3 times the log of x plus 4, then give the domain and range. So for this graph, that 3 is on the outside and that 4 is on the inside of the log. So things on the inside of the log are going to be horizontal. We always do horizontal first and then vertical. So for this one, we know that the transformations that we're making, if it's x plus 4, that means we're going to the left 4. So we're going left 4, and then that 3 on the outside is a vertical stretch by a factor of 3, because remember, the horizontal changes are opposite of what we think. So these are the transformations, and then we want to talk about the domain and the range. So the domain value, remember, anything that we take the log of has to be greater than 0. So you can actually take what's inside the log, so x plus 4 has to be bigger than 0 because we can't take the log of a negative number or 0. So if you just solve this equation, you get x has to be greater than -4. So if we write that for our domain, that means we have -4 to infinity. You could also think about a graph of this and just draw a quick sketch. So if I draw a quick sketch, what happened? We moved our graph to the left 1, 2, 3, 4 from our parent graph and then vertically stretched it by 3. So it looks something like this. It's not the perfect graph, but it's kind of just a rough sketch. So as you can see, your domain would now be, because when you're moving it to the left, -4 to infinity. The range for these is always going to be all real numbers. So let's go ahead and look at the next one. For the next one, you have to be careful because notice what's in the inside of the natural log, in this case, is not written in order, so I would actually rewrite that. So we have y is equal to the natural log of -x plus 2 minus 3. And then, of course, remember, you always want to factor out your b value, so y is equal to the natural log of -1 times x minus 2 minus 3. And so we have our horizontal transformations. So the first one is that -1. So remember, that is a reflection over the y-axis. That 2 is going to, because it's -2, move it to the right 2. And that 3 is going to move our graph down 3 because it's on the outside of the natural log. So that's why we know we're doing a vertical movement. So these are our transformations. Then we want to figure out the domain. So again, for the domain, you can just go ahead and take out what's inside that natural log because it has to be greater than 0. So 2 minus x has to be greater than 0. So if I solve this equation, subtract the 2, so negative x has to be greater than negative 2, divide by negative 1 on both sides. But remember, when you divide an inequality by negative, you have to flip your inequality sign. So my x values are going to be less than 2. So how do you write the domain for x values less than 2? It would be negative infinity to 2. And that makes sense because we reflected our graph across the y-axis. And my range would be all real numbers. And let's just go ahead and look at a quick graph sketch of this. So if I was sketching this graph, notice that my graph moved to the right to reflected across the y-axis. So normally your graph goes this way, but we reflected across the y-axis. So that means my graph is going this way now. And then we're taking that graph, moving it right 2 and down 3. So if I take this graph and move it right 2 and down 3, so right 1, sorry, that was kind of not a very good. So right 2 means I'm moving the vertical asymptote at 0. So 1, 2 would be here at 2, and then down 3. So your graph is going to go something like this. So that should kind of help you visualize. So your domain would be from negative infinity to 2. And again, that's just a rough sketch. So it says find the inverse function of each function below. So remember, to find the inverse, you switch your x and your y, and then you do the order of operations backwards. So switch x and y values, and then PEMDAS backwards to solve for y. So we switch our x and our y's. So this would be x is equal to 3 to the 1/2 power of y minus 7. So you need to, when you're solving for exponential equations, you need to, before you can write it as a log, isolate the exponential part. So I need to isolate the 1/2 to the power of y by doing PEMDAS backwards, because PEMDAS backwards would mean addition and subtraction first. So I need to add that 7 to the other side. So x plus 7 equals 3 times 1/2 to the power of y. Then you get rid of multiplication division, so divide by 3. So x plus 7 over 3 is equal to 1/2 to the power of y. Now we can do our exponent. So to get y out of an exponent, the only way we can do that is to use logarithms. So this in logarithmic form would be the log, the base is 1/2. So the log base 1/2 of all of this over here, x plus 7 over 3, is equal to the exponent y, because remember, the answer to a log is an exponent. And that's how we get y, so it's no longer as an exponent. So looking at the next one that we're going to do, so for this one, same thing. So switch your x and your y. So x is equal to 5 times the log of 3y plus 10, and then you're going to do your PEMDAS backwards. So get rid of addition and subtraction. So x minus 10 is equal to 5 log of 3y. Get rid of multiplication division, so divide by 5. So x minus 10 over 5 is equal to the log of 3y. Now we do exponents, which we don't have, in parentheses. So parentheses means we were looking at this log portion right here. In order to do what's inside of that log, we have to get it out of the log. And how do you get something out of a log? You use exponential form, because that's the inverse. So remember, when the base isn't written, it's base 10. So this in exponential form would be 10 to the power of x minus 10 over 5 is equal to 3y. And then the next step will be to solve for y by dividing by that 3. So this would be, if we divide this by 3 on both sides, we're really just dividing this portion. We don't do what's as in the exponent, so that we can rewrite this as 1/3 instead of 10 over 3 to this power. So 1/3 times 10 to the power of, this would be x over 5, minus, and 10 divided by 5 is minus 2, is equal to y. And so for this last one, if you work it out on your own, if you want to check your work, you should end up with y is equal to 1/2 times 10 to the power of x minus 3, and then plus 1. So you guys can do that one on your own if you need to. For this last problem, we're going to graph a log problem with a transformation. So first thing you want to do is look at your parent graph. So our parent graph is y equals the log base 2 of x, because that would be without any transformation because the base is 2. If it was base 3, we'd use 3. If it was 4, we'd use 4, etc. We know that our reference points for base 2 would be the log base 2 of 2 is 1. The log base 2 of 1 is 0, and we do 1 over the base, so the log base 1/2 is -1, so we can use these points. So we have the points here, here, and then 2, 1. Because this is base 2, if it helps you to think about the exponential form, 2 to what power, so that is going to be switched when you equals y, so you switch it when you do your logarithm. So we know that if we have 2 to the power of 3, 2 to the power of 3 we know is equal to 8. So that means the log base 2 of 8 equals 3. And same thing if we did 2 to the 4th power, we know is equal to 16. So that tells me the log base 2 of 16, sorry, is equal to 4. So 1, 2, 3, 4. So you can use these points to help. So the 2 to the 5th power is 25. So the log base 2 of 25 is 5. 1, 2, 3, 4, 5. So if it helps you to plot more points, that's fine. And so this is our parent graph here. And then we have to, and this of course is the asymptote, do our transformations to our parent graph. So what are the transformations? So we always want to do horizontal ones first. We're moving it to the right 3. Then we're going to vertically stretch it by 2. And then we're going to move our graph up 1. So to move it to the right 3, actually just use green. So that means that asymptote's also moving right 3. So 1, 2, 3. So it's going to be here. And so all these points move right 3. So 1, 2, 3. This point would be here. 1, 2, 3. 1, 2, 3. And that one's going to be off, so we'll just leave that. So that was right 3. So we just did that. So the next one we're going to take a look at is, actually let's do, orange might be too close to red. So let's do a lighter green. So for the next one, we're going to move or do a vertical stretch by 2. So vertical stretch by 2 means, remember that you're multiplying or changing your y values. So 0 times 2 is 0. -1 times 2 is -2, so that point moves down here. 1 times 2 is 2, so that point moves up. And this is 3, so 3 times 2 gives me 6. And this is 4 times 2, which is 8, so 6, 7, 8 would be here. And so this would be my graph with a vertical stretch by 2. And then the last part would be just to move it up 1. So this would move up to here, this moves here, and this would be off my graph up there. So this would be the transformations made to my parent graph, which is y equals log base 2 of x. So the vertical asymptote is now at x equals 3, which means our domain is now from 3 to infinity. And of course, the range is all real numbers for our logarithmic function. And that will conclude this lesson. So it might have seemed a little fast, but again, it is a review of everything that we've learned. So we just kind of have to make sure we know how to go from one form to the other, and that logarithmics and exponential functions are inverses of each other.